Hello everyone, this is Lecture 4 of ComSci 174, Image Classification. In this video, we will discuss image classification. We will introduce machine learning, the importance of datasets, how to evaluate classifiers, and we will also look at some machine learning algorithms. Okay, so let's start. So what is image classification? So in image classification, you are given an input image and you assign one label for the image from a fixed set of categories. So you're going to classify the image. So image classification is one of the core problems in computer vision. So it's important that you know how to do image classification. So examples of image classification could be as simple as binary classification, when you're just classifying between two things. So it could be like hot dog versus not hot dog. Okay, so if you saw the TV series Silicon Valley, one character there, Jin Yang, tried to create like a hot dog versus not hot dog classifier. So it could be as simple as that. It could be like cats versus dogs classifier. Okay, it could also be multi-class, like 3 or more classes. So in this one we have 4 classes, or it could be 10 classes, or it could even be more than that, like 1,000 classes. Okay, so this one is already very large scale because you have 1,000 different classes that you can classify for your classifier. Okay, it could also be something like a fine-grained classification, like for example dog breed classification. So they're all of the same type, like they're all dogs, but then you try to classify it even further based on their breeds. Okay, so that could also be one example of a classification problem. Classification also has some related tasks in computer vision, like object detection. So before you can classify, you might want to detect the object first. Object recognition and image classification is more or less the same. Segmentation also, so you might want to outline the image object first before you can classify it. So some computer vision tasks can be reduced to image classification. Okay, so yeah, that's how important classification is as a task in computer vision. However, of course, the big problem or the big challenge is that there's a large semantic gap between what the computer sees, which is just a bunch of numbers, right? So an image is just a bunch of numbers or a bunch of brightness, intensity values, and it's a huge leap from this bunch of numbers to actually classifying that, hey, this is a cat, or whatever, this is a dog or something. Okay, so there's a huge leap from a bunch of numbers to classifying that this is a certain type of object. So other challenges include viewpoint variation. So if you have if you take the picture based on different like angles or distance, then you'll have a different pose for the image. So it could be difficult to have like a template of what a dog looks like or what a cat looks like. And then if you have varying illumination conditions, of course the image will also look different. Like this is the same image or this is the same object of a bunch of penguins, but then based on different lighting conditions, they produce different images. You also have like scale variation. Like if you only have one image, you cannot estimate the distance just by having that one image, because you're not sure if this laptop is really small or is it really far, or if this laptop is really huge or is it actually just really close to the camera. Okay, and then of course there's also deformation, like changing in pose, occlusion, like being hidden in the background, and similarly you have background clutter, like what if the background kind of camouflages the object that you're interested in, just like here in this example. So you have a cat with some spots, and then you it's kind of lying down on a rug, I guess, that has like a leopard print. So it the cat kind of blends in with the background, so it's kind of difficult to classify whether there's a cat or just pure background. And even with the same class, it could look different. Like there's intra-class variation. So if we have like a category like a chair, but then a chair kinda has different looks. Like it could look like this, it could look like this, and so on. Okay, so there is no like one template image of a chair that could be a good enough model for every chair out there, right? So those are some of the challenges in classification. And so what we're trying to create is something called an image classifier. So our input, of course, is an image, and the output would be the class label, which is selected from a fixed set of labels. So if you're trying to do like a binary classifier, then there are only two possible labels. And then if it's a multi-class classifier, then maybe like a 5 class or 10 class or 1,000 class classifier. Okay, but how do you actually classify the object? So as we mentioned, it's a huge leap from the bunch of numbers to the class label, right? There is no obvious way to hard code the algorithm, because even if we have like template objects of the classes, based on the challenges that we showed earlier in the previous slide, it would be difficult to just have like a general like look for that certain class, right? So there's no obvious way to hard code the algorithm. Like a dog is like fluffy or has a fur, has 4 legs, has ears and eyes and nose, but then the same description could also fit the cat, right? A cat also has fur, has 4 legs, has nose, eyes, ears, and so on. So it's kind of difficult, right, to just have like a hard code or like a step-by-step like algorithm to classify a certain object. So instead of doing that, we will take the data-driven approach. Okay, so what we will do is we will collect a data set for the intended classes. So we'll have images of different classes, and of course their labels. So we need to label these images that, like, this image is an image of a cat, this image is an image of a dog. Okay, and then we'll use machine learning to train our classifier, and after we train our classifier, we will evaluate its performance on unseen images to make sure that it really is it really has learned something and can generalize even to images that it hasn't seen before. Okay, so because we will use machine learning to train our classifier, of course we will need to introduce machine learning. Okay, so the main focus of this lecture is actually to introduce you to machine learning in relation to image classification. Okay, so I'm sure you've heard of the term machine learning before, but what is machine learning formally? So Arthur Samuel in 1959 said that machine learning gives computers the ability to learn without being explicitly programmed. Okay, so it can learn without being explicitly told that, hey, this is a cat, this is a dog. Okay, it can just learn through training. Okay, so an example of that could be like if you have image of handwritten numbers like this, 6715884, and then you have a machine learning algorithm that will learn that, hey, this is a 6, this one is a 7, this one is a 1, and so on, without explicitly saying that if it's just a straight line, that's a 1, if it's like a horizontal line with a slant, that's a 7, and so on. Okay, so you don't have to hard code some rules or some templates to come up with the classifier that will tell you what that handwritten number is. So the machine learning algorithm will do that for you. Okay, you can also do it for spam classification of emails. So you have a bunch of emails that are classified, pre-classified as spam or not spam, and then you have a machine learning algorithm to learn the contents of what makes up a spam image. So what are the common properties of spam images and not spam images, or not images but spam messages and not spam messages. So later on, when you have like a new email message, it can already classify whether that is spam or not. Okay, so yeah. And then Tom Mitchell in 1997 also said that a computer program learns from experience E with respect to task T and some performance measure P if its performance on the task, as measured by the performance measure P, improves with experience E. So basically, he's saying here that machine learning has three components. So the task itself, okay, so what are you trying to do? The experience, which is basically training, okay, and the performance measure, so the evaluation metric that you're going to use. And he's saying that if you are improving on your certain task by adding more experience, by adding more training, and you can measure that improvement by using the evaluation metric, okay, then you are learning. Okay, so the more you train, you have better performance, so that means that you are learning something. Okay, so that is machine learning according to Tom Mitchell. So there are two main branches or two main types of machine learning, and that is the supervised and unsupervised learning. Okay, there are other types as well, but these are the two main ones. Okay, so in supervised learning, our input would be labeled data samples. So you have the pair X and Y, wherein X is the data and Y is the label. So that means that all of your data samples have like a corresponding label or answer. Okay, and for supervised learning, we usually have two tasks, which is classification. Okay, so this is where image classification comes in, and the other one is regression. So for classification, this is usually used for discrete variables, so you have discrete set of classes, whereas in regression, this is used for continuous variables, or if you are trying to like project what the value of a certain data point is given these properties. Okay, but we'll focus on classification in this lecture. On the other hand, there's also unsupervised learning. In unsupervised learning, your input is unlabeled data. So you only have data samples, but there is no labels. Okay, that's why it's unsupervised, because you don't have the labels. So what can you do with unsupervised learning? Well, you can find patterns in the data. You can do clustering. Okay, you can group them to group together similar data points, and you can also do association. Okay, so those are what you can do with unsupervised learning. But for this lecture, we will focus on supervised learning, specifically classification. Okay. There are also other types of machine learning, like semi-supervised learning, wherein some of the data is labeled, some of the data are not. And there's also reinforcement learning, which is used for games. When you're creating like a bot for games, then reinforcement learning is used. Okay. So as I mentioned, we will focus on supervised learning in this lecture. So just a quick example, or like the difference between classification and regression. So in classification, you have a certain set of data points like green versus red, and your classifier will try to divide the data points cleanly. Okay, so you can divide them by having like a line that separates the red from the green. Whereas in regression, you have certain data points, and your model will try to fit a line that best describes these data points, so that later on, if you have like a new data point, you can predict what would be the, like if you have the value for X, what would be the value for Y. So for example, if you have like a model for predicting the prices of a house based on, let's say, certain properties like square, the area, the lot area, or the number of rooms, or like if it's gonna if the location is like near the center of the city, or is it in the outskirts of the city. So using those certain properties, you can use them to estimate like the price based on your regression model. Okay, so those are just some of the differences between classification and regression, but as I mentioned, we'll focus on classification. Okay, so in classification, specifically in supervised learning, so what will happen is you have a bunch of training data. So for example, this is a duck, this is a duck, this is not a duck, this is not a duck, and then you'll feed that to your supervised learning algorithm to produce like a model, a predictive model that will later on be used on real data. Like for example, this one hasn't been seen before, and if you feed it to the predictive model, it will predict that it is a duck also. Okay, the same thing you can do with handwritten digits. So you have labels like this is a 5, this is a 0, it's a 4, a 1, a 9, and so on. And then using this data with labels, you can teach your classifier what certain digits are, and then that model will be used to predict handwritten digits later on. So the analogy for supervised learning is like you're teaching a child like the alphabet. So you're teaching a toddler like this is letter A, this is letter B, this is letter C, and so on. And then you do that by repetition. So you teach them these letters today, and then on the next day you follow up and teach them again to make sure that they don't forget. Okay, and then how do you make sure that they are really learning? Then you give them a test later on and see that well, he or she is really learning that this is an A, this is a B, this is a C, and so on. And you do this because there are labels with the image. So you are telling like the child that this, hey, this is an A. So that's similar to telling the classifier that, hey, I'm showing you this image and this is of a certain class. So this one is an image of the letter A or the letter B, and so on. Okay, so that's the analogy for supervised learning. Now we have the workflow for supervised learning. So you have the data here that's divided into the training set and the test set or the validation set, and the training set is fed to the learning algorithm, and then it will try to learn the model, and after that it will be fed to the evaluation using the validation set, and through the evaluation it will figure out whether, hey, is this a good enough classifier already, or should we continue learning? So if it's not good enough yet, then we will go back to the algorithm and retrain it, tweak some parameters, and then loop it back to the evaluation. And then once it has found that, hey, this is already a good enough classifier, then you'll produce the final model. And this final model is what you'll use to classify real world data. Okay, so you'll use the model to actually have your predictions. Okay, so that is the general workflow for supervised learning. So what are the three main ingredients for supervised learning? So number one is data. Okay, so this is a data-driven approach, so you need lots of data. Okay, next is of course the training algorithm that you'll use, and then the third one is the evaluation metrics. So how do you figure out that you're actually doing good? Okay, that the classifier is doing well. So we'll learn some evaluation metrics later on. But first, let's start with data, because data is king in machine learning. Okay, so data is the most important thing in machine learning, and it's not the algorithms. So no matter how good your algorithms are, if your data is terrible, then your classifier will also not do as well. Okay, so the more data usually translates to better performance. Like if you have a lot of data, then your training would be generally better because you have a lot of data points to learn from. And I also like to add that you also need good quality data, because even if you have a lot of data but then it's terrible, like it doesn't really help the process of learning, then it's also not effective, right? So more good quality data is equal to better performance. Okay, and of course in image classification, our data refers to images and the labels, because of course we are doing supervised learning. Okay, so the images need to have the pre-assigned labels. So this is an image of a dog, this is an image of a cat, and so on. Okay, so let's now look at some of the benchmark datasets in image classification. So first we have the MNIST dataset, which contains handwritten digits from 0 to 9, and it has around 70,000 samples. Okay, so there's a lot of handwritten digits in this dataset, and this is kind of a historical dataset because it's been around since I think 1990s, and it was used for like creating a classifier to recognize the digits in like bank checks. Okay. Next we have Pascal VOC dataset. So it contains 20 classes with 10,000 images. So these are the 20 classes. So you have airplanes, bicycles, birds, boats, and so on. Next we have the Caltech 256 dataset, which has 256 classes and around 30,000 images. There's also a Caltech 101 version. It only has 101 classes. So yeah, this is another benchmark dataset. And then you also have the CIFAR 10 dataset, which only has 10 classes but 60,000 images. So even if there are fewer classes, this has more images than your Caltech 256. So this one is better in terms of the number of like images that you have in the dataset itself. So yeah, these are the 10 classes, and this one is a popular benchmark dataset for image classification as well. And then of course the most popular one these days is the ImageNet dataset, which contains 1,000 classes with around 1.3 million images. Okay, so there's a competition for ImageNet dataset. So people would compete to have the best classifier performance on this dataset with 1,000 different classes. Okay, so yeah, those are some of the benchmark datasets for image classification. Now, for our data, we usually divide it into 3 sets, which is the training set, the test set, and the validation set. Okay, and the usual data splits are 70 15 15, 70 20 10, and then 80 10 10. Usually 70 or 80% of the data set is allotted for the training set because that is the most important one. And then you have either 15 15, 10 10, or 20 10 split for the test set and the validation set. Okay, so let's take a look at what each data set means, or what is it supposed to do. So let's start with the training set. So this is the data set that's used by the algorithm during training. Okay, so in training the classifier, the training set is what is being used by the algorithm. So the classifier learns from these data samples. Given the image and the label, it will try to figure out the connection of certain properties of the image, certain features of the image that makes this certain label. So it will try to learn the features of a dog, features of a cat, features of an airplane, features of a bike, and so on. So whatever the different classes are, it will try to learn these different features from the training set. Okay, and it usually takes up the bulk of the data set. So majority of the data set is allotted to the training set, so around 70 to 80%. Okay, so examples, as I mentioned, were the MNIST data set. Okay, so the classifier, or the algorithm that trains the classifier will look at this and see that, hey, this is 5. Compare that with this one, which is 0, this one, which is 4. So it will try to figure out what are the features that makes it a 4 or a 1 or a 6 or a 9, and so on. Okay, next is the test set. The test set is used to evaluate the performance of the classifier after training. So once you are done with your training, you're satisfied with your model, your classifier, then you test it to see how good it is. Okay, so it should answer, you should ask yourself, does your classifier generalize well to images that it hasn't seen before, because maybe your classifier is doing too well on the training set, but in reality it's just like memorizing the training set. But if you ask it images that it hasn't seen before, it will not do too well, because what it's doing is not learning but just memorizing. Okay, so you should also test the performance of your classifier after the training. Okay, so this is actually the most important part, right? Evaluating after training. So just like this. Okay, so we've used this 4 images in training. Okay, so later on, after we have created our predictive model, we should also test it on an image that it hasn't seen before, and make sure that it also does well on the test set. Okay, and then the final one is the validation set, which is similar to the test set, but it's used during training, because the test set is used after training, right? So the validation set is like a test set, but it's used during training, and it's used to estimate the classifier performance during training. So you use this to determine whether to continue or to stop training. So you train the classifier using the training set, right? So after that, you use the validation set to like evaluate the performance of the classifier, and if it's already good enough, then you stop and make that the final model. But if it's not yet good enough, like based on the validation set, you continue the training and loop it back to the training part. Okay, so the validation set is like a test set, but it's used during training. So how are the two different? Okay, how is validation set different from the test set? So both are held back data. They are not used in the training set, but the difference is that the validation set is kind of a biased evaluation, because the model kind of sees it during training. Like, it doesn't use the validation set in the actual training itself, but because it decides whether to continue training or not, then you might become biased to the validation set. Okay, so it might like learn about the validation set also. Like it kind of tunes the training to the result of the validation set. Okay, whereas the test set is totally unbiased, because it will not be seen at all during training, and you only use it after you have the final model, and then you test it on that. Okay, so the test set is the actual unbiased evaluation, whereas validation set is kind of a biased evaluation, because you kind of see it during the training. Okay, now sometimes we also do something called cross validation, and what we do in cross validation is you divide the training set into k folds or k partitions, and during validation you use a different fold, or you use a different partition for the validation set. Okay, and then in the next iteration you use another fold for the validation set, and you usually do this when the data set is small. So when you only have a few images and you cannot afford to like have a separate validation set, because it would take away from the training set. Like, you need as many images in the training set as possible, right? So if you like use a separate validation set, then it would take away from the training set. So if you have that situation that the data set is small, then you use cross validation. However, the drawback is that it's computationally expensive, because what you'll do is, for example, in this one, this is the training set, so you divide it into different folds. In the first round, you can maybe use this one, the orange part here. You hold it out, you take it out of the training set and use it as the validation set. And then on the next round, you use the second fold as the validation set, so you don't use it for training, and then you use that as the validation set, and so on. So you use a different fold each time, just so you don't have like a separate validation set that's being set aside. Okay, so you kind of use up all of the different folds as the validation set. So like, you're interweaving the training set and the validation set in cross validation. Okay, and you do this again if you only have like a limited data set size. Okay, so that's cross validation. Now let's go to the next part, or the next ingredient of classification, which is evaluation. So evaluation is basically just testing how good the classifier is. So you need to know if your classifier is doing well or not. Okay, and evaluation is can be summarized in the following 3 lines of code. So for each test set point, okay, so you have the data and the correct label, the true label of that data point. Okay, for each of those data points, you will use the model to predict a label for the data, and that would be the predicted label. And then you'll compare whether the true label, or the correct answer, and your predicted label, which is your model's answer, is the same or not. Okay, so you do the comparison, and then you figure out how many labels you predicted correctly or not. Okay, so that is the gist of evaluation. Now there are 3 different types of errors that we are interested in, and they are kind of related to the 3 different types of data sets. So you have the training set, validation set, and test set. So you also have the training error, test error, and validation error. So let's start with the training error. The training error measures the classifier performance on the training data. So you basically evaluate how well your classifier is doing on the training set, right? But this is not actually that important. You can choose not to focus on this, because if you have a low training error, like for example, you are classifying 99% of the training set correctly, that could mean 2 things. It could mean that you really have a good classifier, which is, well, what you want, but it could also mean that you have an overfitted classifier. Now, what is overfitting? What does an overfitted classifier mean? Well, in overfitting, you kind of do this. Okay, so in overfitting, you're trying to force or focus too much on the training set, and make sure that you are having the best results for the training set, and you're force fitting your model towards this data set. But usually when you do this, you are not generalizing. So in this in this illustration, so this set of data sets could the best possible model for this would have been this curve, right? So there are only 2 wrong classifications. Like inside this curve, you have all circles except for these 2 x's here, and then all the other x's are outside. Okay, so if you're the opposite of overfitting is underfitting. So if you're underfitting naman, you are kind of simplifying the model too much. Like you're making it too simple, such that there's a lot of wrong answers as well. Okay, so if you're underfitting, maybe you're just content with having this line as the division. So there's way too many wrong answers. Like you have this x, you have 1, 2, 3, 4, 5, 6, 7 x's on the wrong side of the line. Then you also have the 2 circles on the other side of the line, and then you have the other circle here, which is like straddling the line itself. Okay, so underfitting is also wrong, because you are that means that the classifier is underperforming, or not explaining the division as well as it should. Okay, so this one is the best fit maybe, but if you're overfitting, you're kind of like force fitting it too much. Like you're really doing the complicated curves here just to make sure that x is belonging on the other side. So you're trying to focus too much on the training set, that maybe it doesn't really generalize to the real world data or the test data later on. Okay, so another example of the overfitting versus underfitting is something like this. So underfit is something like a straight line here, wherein the just right the correct fit would have been something like a curve like this. And then if you have the overfit, then you're complicating your model too much by making all of the data points actually align with your model. So overfitting is doing too much. Okay, so be careful when you have like a very low training error, because for one, it could mean you have a good classifier, but it could also mean that you are actually overfitting your classifier. Okay. Next is the test error, which measures how well the classifier generalizes to unseen data, and this is the most important one. Okay, this is what you want. You want the test error to be as low as possible, because the test set hasn't been seen before, right? So if the classifier hasn't seen it and it's also doing well on the test set, then that means that you really have a good classifier. Okay, the classifier really learns something and can generalize even to data that it hasn't seen before. Okay, so if you have a low test error, that means that you really have a good classifier. Now, how about the validation error? The validation error kind of estimates the test error during training. Okay, so you use the validation error to adjust model parameters during training and to decide whether to continue training or to stop the training already. Okay, so validation error is also important, but again, we mentioned that the validation set is kind of a biased evaluation. So the most important error is still the test error. Okay, now here's the golden rule in machine learning: do not use test data in training, because that is cheating. Okay, so basically you can think of the test set, the validation set, and the training set as like having an exam. So the training set is like the lecture notes, the lecture video, the lecture materials that you study for the exam, right? The validation set maybe is something like a mock exam, or like um, uh, an example exam from previous years that you can use, but it's not the actual exam itself, right? And then the test set is the actual exam itself. Okay, so do not use test data in training, because if you do that, it's like cheating. It's like you obtain the actual test exam, or the exam itself, and then you use it for training. So you kind of studied already what will come up in the exam. So don't do that, because it's cheating. Okay, now in binary classification, we usually since we only have two classes, right? It's either the this or that. So it's either the positive or the negative. So it's either 1 or 0. So in binary classification, we usually have 4 results in evaluation. So you have the true positive. That means that the correct answer is 1 or positive, and the predicted label is also 1, which is also positive. Then you have the true negative, wherein the correct answer is 0 or negative, and the predicted answer is also negative. So we want these two. We want true positives and true negatives. But there are also false positives. So false positives occur when you have the correct answer is supposed to be 0 or negative, but then you predicted it to be positive. So that is a wrong positive prediction. So it's a false positive. Okay. And then so you have probably encountered this with like testing, with COVID testing or pregnancy testing, right? A false positive is when you don't have COVID, or you don't have you're not pregnant, but then the test kit shows that it is positive, right? So that is a false positive. And then there's also false negative, like the correct answer should have been positive, but then you predicted a negative. Okay, so it's also the opposite, right? So those are the 4 possible results when you have binary classification. So let's now go to our evaluation metrics. So what are the actual scores that we can use to evaluate our classifier, to let us say that this one is doing well? So what are the actual metrics? What are the actual scores or numbers that we can use. So first is, of course, accuracy. So this one is very common. So it's just a percentage of correct answers, right? So the correct answers versus the total possible answers. Okay. In terms of the true positive, true negative, and so on, it's just the set of the number of true positive plus the number of true negative divided by the total amount of data set or the data points. Okay, so that is accuracy. That's the most common one. But we also have precision and recall. Okay, so what is precision? Precision is the percentage of correct positive predictions. Okay, so to compute precision, you have the true positives divided by the true positive plus the false positive. So what does this mean? Out of all the positive predictions that you had, how many were correct? Okay, so diba you predicted positive for true positive and the false positive. Okay, out of all of those that you predicted positive, how many were actually correct? So how many are the true positives? So that is precision. And for recall, it's the percentage of positive samples that were correctly classified as positive. So how do you compute recall? It's true positive divided by true positive plus false negative. Okay, so you're interested in the actual positive samples. So that would be the true positive and the false negative. So because false negative, it's supposed to be positive, but you predicted negative, right? So you were wrong in that case. So this is still a positive sample. So out of those positive samples, how many did you classify correctly? Okay, so that is precision and recall. So to illustrate it better, we have this diagram. So supposedly the data points should be divided by this line here, because you have the dark data points and then the light data points. So you have the white and the dark ones. But then let's say that your classifier drew a circle to divide them. So those inside the circle are positives, those outside are negatives, when supposedly the division should have been this line, right? So the true positives are the ones that are inside the circle but are also on the left side, and then the false positives are the ones that are inside the circle but are supposed to be on the right side, because they should have been negatives, right? They are white, okay, but they fall inside the circle, so they are considered positive by your model. Okay, then you also have false negatives here and true negatives here. So for precision, how many of the ones that you are selecting as positive, so those that are inside the circle, are actually positive items? Okay, and then for recall, that would be how many of the actual supposed to be positives, like the ones that are on the left side, are included in your predicted positives. Okay, so that's the difference between precision and recall. Now if it's still not clear, let's show more concrete examples. So let's say that you have a dog versus cat classifier, and your interest point is the dog. So meaning we consider dog as the positive and cat is the negative. Okay, so in precision, you ask yourself, out of the samples that you classified as dog, how many are actual dogs? Okay, so out of those that your model labeled as dogs, how many were actual dogs? That is precision. Okay, in recall, out of the actual dog samples, how many did you classify as dogs? Okay, so that's the difference. Okay, now another example is for spam classifier. For precision, we are interested in the question, out of all that you predicted as spam, how many were actual spam? Okay, and then in recall, out of all the actual spam messages, how many did you predict as spam? So that is the difference between precision and recall. Hopefully that is clearer now. Okay, now since we have two metrics that are related, what do we want? between precision and recall. Of course, we want the high precision and high recall because you are already very precise and you also recall a lot of the positive labels. So this one is very good. Okay, high precision, high recall, that's very good. If it's low precision and low recall, that is very bad. You don't want that. Okay, but what if it's already it's a mixture? What if it's high precision, low recall, low precision, low precision, high recall? What if it's a mixture? For low precision, high recall, this one is you can think of the classifier as being very aggressive. Okay, and why is that? Because it returns many positive answers, like it has high recall, but most of them are wrong, so it has low precision. Okay, so it follows the mantra, more entries you send, more chances of winning. So it always gives out a positive classification, so that's why it has high recall, because you can hit on as many positive answers as possible. But it also has low precision because the more positive answers that you send, there's also a high chance that you will have a wrong answer because you have negative data points as well, right? So an example of this is a classifier that mostly predicts spam. So it has high recall because a lot of the actual spam is being predicted, right? Because you mostly predict spam. Like let's say 95% you predict spam. So if it's an actual spam message, then you can really more or less predict it as spam. But it has low precision because a lot of the not spam folders or the legitimate folders are also predicted as spam. So a lot of the important emails end up in the spam folder. So this might not be what you want. So it's too aggressive. Okay. Now, how about the opposite of that? What if you have high precision but low recall? Now, for this one, you can think of it as a very conservative classifier. It's really careful. Okay, it doesn't return too many positive answers, but if it does, it's mostly correct. Like it only predicts positive. If it's like really sure, or it's there's a high likelihood that it really is a positive answer. Okay, so it's too conservative. So an example of that with the spam classifier again is that it rarely predicts spam. So it has high precision because when it does predict when it is a spam, okay, because of the rare prediction of spam, then that means that it really is sure that that is spam. So you have high precision. You're not just willy-nilly classifying every message as spam, right? But a lot of spam emails end up in the main folder, so you have low recall as well. So your spam folder does not recall as many spam messages as possible. Okay, so you kind of don't want this as well, because then your spam filter is not doing too well, because a lot of spam emails end up in the main folder. Okay, so that's the difference between precision and recall. And well, it's up to you if you have like if you want this version, the aggressive version, or the conservative version. Okay, so those are evaluation metrics. Now finally, let's go through some machine learning algorithms, and we'll just give like a very brief introduction to some of them. We won't go into the details of each one. I'll just give you the main idea of how each machine learning algorithm works. Okay, so let's start with the naive Bayes algorithm. So in naive Bayes, we use Bayes theorem. I'm sure you've encountered this before from your statistics classes. So in the Bayes theorem, you use the probability of each class, and then the conditional probability, and then the probability of A given B can be computed as probability of B given A and multiplied with probability of A divided by the probability of B, right? So that is where the Bayes part comes in. But why is it naive? The naive part is because it naively assumes that the properties are independent of each other, which is usually not the case. So the properties of the data set or the data point are thought of as being independent of each other, so you can chain them together, the probabilities, which is usually not the case. That's why it's naive. But even if it's naive, it usually works well, especially in text classification applications. So this can be used in spam classification, spam classifiers, text classifiers, like you can predict which author this text belongs to based on the usage of the grammar structure and so on. So this is used mostly in NLP, or natural language processing, the naive base. Next, we have the decision trees. Okay, so decision trees are kind of simple to look at and to interpret, really, because it's interpreted as a tree, right? So in the tree, you have in your inner nodes, you have questions. Okay, so like, what is the outlook? What is the humidity? What is the wind strength? Or what is the age? Is he a student? What is the credit rating? And so on. So in the internal nodes, you have questions. In the branches, you have the answers to the questions. So is the outlook sunny, or is there overcast? Is it raining? And so on. And then on the leaf nodes, or the nodes without children, you have the final labels. So either a yes or no answers here. Okay, so you can use this for like weather predictions in medical. This is also being used in medical classifications, business model or business predictions as well. And the way that decision trees are being made is basically the data set is being divided into two sets, or two or more sets, based on which property divides it well. Okay, so what do you mean by that? So let's say property A divides the data set such that it looks like this. So X, O, O, X, and then O, 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 X. So this is the division if you use property A. And then if you use property B, maybe it's O, 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 X, X, X. It's actually 5 O's. So if that is the division, then which property is better? Well, property B is better because it cleanly divides the data set into two homogeneous sets. Okay, meaning the set this division has more or less the same types of classes, like the O's, and this one is composed of the X's. Now, it doesn't always have to be clean, but whichever property divides it the cleanest, or will win out for this certain like branch here. And then we'll do this recursively until we can build the final decision tree. Okay, so that is how it's being created, like which property will best divide the data set. So if it's this property, then we will divide it on here. Now if it's not like exactly perfect, like let's say there's an X here and there's an O here, then that is still better than this one, because you still have like a lot of chaos here, right? And there's also some chaos here, 3 to 1. So if this wins out and then it's still not perfectly divided, then you divide this again. So what property best divides this one? What property best divides this one? Okay, so that is how decision trees are created. Next, you have the random forest, and a random forest is basically just a collection of decision trees. So that's why it's a forest, right? So you have several decision trees, but the thing is, in random forest, the random part of random forest is because you don't use the whole data set. You actually just use a random sample of the data set. Okay, So instead of, like, let's say 100 data points, you just randomly sample some data points from there, and that's why each each decision tree in the forest is actually different, okay, because you randomly sample the data, okay, to create the tree. And it also usually doesn't use the best split, okay. So some of these could be like, it's not the best decision tree, a standalone decision tree, but the idea is, if you have several decision trees that, even if they're weak, what you do is you combine their answers and you use like a majority voting to predict your final answer. And the idea for random forest is, instead of having like one decision tree that is like optimal, you use several decision trees that are not as optimal, that are like weak compared to the one strong decision tree. And even if they have they are weaker, but there is strength in numbers. That's the basic idea, okay. So you use several classifiers, several decision trees, and then you take a majority vote, and then whichever vote wins out, that would be your final label, okay. So that's the idea for random forest. Now next is AdaBoost, and it has similar to random forest. You have several classifiers here, but what happens in AdaBoost is something like this, okay. So for AdaBoost, you the first thing is you try to train a classifier, and this could be a weak classifier. It doesn't have to be optimal, right? And let's say that this is your first classifier. In this first classifier, you are predicting this 3 data points wrong, right here, because it's on the other side of the line when it's supposed to be on the right side, right? And with this information that I misclassified this 3 data points here, on the next round or on the next classifier, this data points will be boosted. What do you mean by boosted? It means that the next classifier will try to focus on these data points that I misclassified on the previous round, and make sure that on the next classifier it will not be misclassified anymore, okay. So it will focus on this one, and it will produce the next classifier. And so let's say that this is the next classifier here, this is the line. And so in this one, this is also not perfect, it's still weak, and then it has this points here misclassified. So on the next round, it will now boost this data points again and make sure that this data points will be classified correctly, okay. So it will do that, it will again and again until you have like K classifiers already. And even if all of these classifiers are weak, the idea is strength in numbers still. So if you have if you want to classify your data point, you consult classifier 1, classifier 2, up to classifier K, and instead of majority voting like in random forest, they will do a weighted voting, and the weights would depend on the performance of each classifier. So if this one is like really bad, then it will have like a low weight in the vote, and if this one performed pretty well, then it would have a higher weight in the voting, okay. So based on the classifier performance during training, the weights would be adjusted appropriately, and then their weighted votes would be aggregated to form the final answer. Yeah, so that's the idea for AdaBoost. So it's similar to random forest in a sense that it has multiple classifiers, but in the way that it produces the classifiers, it's different, and also in the final voting, because in random forest we just did like a random sampling, okay, but the decision trees are more or less independent of one another. And then in the prediction, we used majority voting, whereas in AdaBoost, the next classifier is actually dependent on the previous classifier, because based on the performance of this one, like which data points were misclassified, I will boost them on the next classifier to make it focus on the misclassified data points. Okay, so they are sequential, so they are related to one another, and in the final voting, they don't take just a majority vote, but they actually do a weighted voting. Okay, so that's AdaBoost and Random Forest. And so those two are actually part of a general technique called Ensemble Method. So in the Ensemble methods, you don't have one classifier only. You have several classifiers, which produces their own output, and then you aggregate those outputs either by majority voting or weighted voting to produce the final output. So and some methods include the bagging, which is what is the technique that's being used for random forest, and then you also have the boosting, which is used by AdaBoost. Okay, so Ensemble method is when you have several classifiers and not just one, and then you aggregate their answers. Okay, next is the k nearest neighbor, and in this one you actually don't do any training, and the idea for this is if you have a data point, you just consult its neighbors for what is the answer, like and the idea is if you consult the nearest neighbors, it's like they are the most similar data points to it because they are the closest, right? So the k here is refers to the number of neighbors that you need to consult. Okay, and then the nearest part means that we need to measure the distance, right? So we usually either use L1 or L2 distance, either the Manhattan distance or the Euclidean distance. So Manhattan distance is basically if this is point A and point B, Manhattan distance is just this one plus this one. Okay, the x plus the y. Okay, that's the Manhattan distance. The Euclidean distance is the straight line distance from here to here. Okay, so that could be different. Okay, so so that is how you measure the distance between data points. So that's why you can say nearest neighbors. Okay, and then the k, of course, is just controls how many of these nearest neighbors you need to consult. So it does not actually train. It carries around the training set during classification, and it's not that efficient in memory and computation compared to the other machine learning algorithms. So how does it work? For example, if you have this one, so if you have like data point here, so what are the 5 nearest neighbors? So you have 1 here, 2 here, 3, 4, and then maybe the next one is this one. So those are the 5 nearest neighbors, and then you take a majority vote, so you have 4 blue votes and 1 red vote, so this one is still classified as a blue. Okay, and then even if you have something right here, so the 5 nearest neighbors would still be 1. Okay, let's reset that. If you have the point right here, the 5 nearest neighbors would be this one, this one, this one, this one, and then that one. So you still have 4 blue votes versus 1 red vote, so that would still be a blue vote. Okay, so that is how k nearest neighbors work. You consult k of your nearest neighbors, and then nearest being defined by the distance metric, and then you decide based on those neighbors what should your class be. Okay, so it's like peer pressure basically. Okay, so some examples of k nearest neighbor in image classification would look something like this. So it could work, but it's not too effective because if you just use pixel based distance, it could mess up a lot. Like for example, if you shift the picture to the left, then the distance would already be different, right? Or if you add like black patches here, then it would also mess up the distance, and if you darken it, it would also mess up the distance. So k nearest neighbors is not really suitable for image classification just because it can be messed up. The distance can be messed up even by slight alterations. But this one can be used for like text based data or like numerical data. K and N. So it still has applications, but not so much in images. Okay. Now the next one is support vector machines, and this one is a really popular machine learning algorithm. And the idea is, for your data points, you kind of plot it in n-dimensional hyperspace, where n is your number of properties. Okay, so to make our illustration simple, let's say that we only have two properties. So we can plot it in a two-dimensional space. You have your x and your y. Okay, so let's say that these are our data points and their classes are either a circle or a star. So what a support vector machine does is it will create like a hyperplane, or in this case a line. So we call it a hyperplane because we're not really sure of the number of dimensions. So if n is greater than 2, then it could be 3-dimensional or 4-dimensional and so on. So it's a hyperplane. But let's say that we only have 2 dimensions, so it could just be a line. So this hyperplane, or this line that we'll create, would try to maximize the margin between the closest points to the line. Okay, so let's recap that. So in this one, or going back here, we're only interested in something called the support vectors. So it's actually this one, and this one. Now what are the support vectors? The support vectors are the points, or the data points, that are closest to your hyperplane or your line here. So these are the closest points to the line, right? So we're not really interested in the rest of this. We're only interested in the support vectors. Okay? And our goal is to maximize this margin here from the line to the support vectors. So we want to maximize this as much as possible. Now, another plane would have been something like this. Okay, so let me draw maybe a blue plane here. Okay, so what if our line looked like this? Okay, so this might be another division. That is still a valid, or that is still a correct division, right? Because everything to the left is all stars, everything to the right is all circles. However, what would be our support vectors in this case? That would be this one and this one versus this one and probably this one. But the margin here is too close, right? Like for example, this support vector is too close to the line. And the idea is we want the maximum margin here so that we have the maximum room for error. Okay? If it's too close, even if it perfectly divides the two data set, that's probably not optimal, because maybe our test set has somewhere here. Okay, so this is already wrong, right? But if we had this maximal plane here, it would still be correct. Okay, so that's the idea for support vector machines. You create the hyperplane, or the line, that best divides your data points by making sure that the support vectors, or the points that are closest to the hyperplane, has maximum margin. Okay, that's the idea for support vector machines. And then next we have neural networks, which is patterned after our actual neural networks of the human body. So you have neurons here. So these are neurons. Okay, the circles here are neurons that are connected to each other. And so you have the input layer that's connected to another layer, and then this layer is connected to the next layer, layer 2, and then the layer 2 here is connected to the final output layer, which will give you our final answer. So the neurons are trying to learn which connections or which properties are connected to other properties and how are they related. Okay, so these connections are controlled by weights, and those weights are what's being learned during training. Okay, so we'll actually learn more about neural networks in our next video, because we will dive deeper into convolutional neural networks. So we will talk more about the details of neural networks in our next video. But for now, uh, just know that neural networks are composed of like neurons, and then they're trying to learn the weights or the connections between one neuron to another. So maybe I don't need the connection from this node to this node. Maybe I want to maximize the connection of this node to this node because that is a really important connection, and so on. So that is what's being determined during training. Okay, so that's neural networks. And then for deep learning, which is kind of like the buzzword or the popular technique for image classification these days, a deep neural network is basically just a neural network with 3 or more hidden layers. So going back here, the hidden layers are those that are not the input layer or the output layer. So everything in between is called a hidden layer, and those are the layers that learn the connections between different properties. So if you have a deep network if you have 3 or more hidden layers, right? So deep learning is basically just neural networks on steroids. You have just more hidden layers. Okay, so we'll learn more about this in our next video, which focuses on convolutional neural networks and deep learning. Okay, so that's it for the machine learning algorithms. So finally, let's go through the image classification pipeline, or what is the step-by-step process in creating or in classifying an image. So given your input image, first you usually pre-process that to make sure that we're working with a good image. So if you might blur it, or you might resize it, or whatever you want to do. And then after that, if you have the pre-processed image already, you get the features. Okay, features of the image, like you can use HAR or the HOG or SIFT or SURF features. So you'll learn more about feature extraction, feature matching in some of your reports. Okay, so once you get these features, okay, you don't use the actual image itself, you just use the features that you extracted from the image. These features are what you feed to the learning algorithm. So the learning algorithm could be an SVM, a random forest, a neural network, and then that is when you learn your classifier, and you use that to get your label assignment. So it could be a cat or a background or whatever. Okay, so that's the pipeline for image classification. Okay, so again, to review, the learning workflow for classification or for machine learning or supervised learning in general starts with data, which is divided into the training set and the validation set, and you use the training set to train the algorithm for the classifier, and then you pass it to the evaluation. So the validation uses the validation set and figures out whether to stop training or continue training, because if it's not good enough yet, then we'll loop back to the algorithm to continue training, and then it will loop and loop here until we have figured out that, hey, this is already a good enough model, so we can have our final model here, and we'll use this final model for our production data, which is like the test set or the actual data that you'll classify. Okay, so that's the workflow for supervised learning. So that's it for this video. So to summarize, we learned about image classification, which is giving a label from a fixed set of categories to an input image. Okay, we learned about machine learning, which is about the computer learning without being explicitly programmed, and it has 3 components. You have the data itself, the evaluation metric, and the machine learning algorithm. So we learned about the importance of data sets, how they're divided into 3 sets. You have the training set, test set, and validation set. And the golden rule again is don't use your test set in training, because that is cheating. And of course, you need to evaluate the performance. So we introduced evaluation metrics such as accuracy, precision, and recall. Okay, and then we looked at some machine learning algorithms. We introduced some of their concepts, and then in the next meeting we'll learn more about or in the next video we'll learn more about the neural networks and convolutional neural networks in specifically. Okay, so convolutional neural networks are what's being used nowadays for image classification. So we'll dive deeper into those models next time. Okay, so that is it for this video. If you have any questions, please don't hesitate to ask me. I hope you learned something new today. Hope you learned something about machine learning, and even if this is not a machine learning class, hopefully the lessons that you learned from this video can be used later on in when you work in the industry, because machine learning is very important nowadays. Okay, so if you have questions, please don't hesitate to ask me, and I will see you in the next video.